So I'll talk about some equilibration of a classical harmonic chain, and this work is being done, ongoing work, but with Saurabh Pandey, who is a Dutch student at ICTS, and Abhishek. It will arrive soon on archive. Yeah. Okay. So consider two bodies at different temperatures, and if you bring them in contact, then there will be heat flow across them, and after a long time, they come to a thermal equilibrium, and this is a kind of quite common phenomena. And natural question that you would like to ask is what is the final state, and how does the system relax to the final state? So such a question in the context of non-integrable macroscopic system one can answer, and in such systems one often expects that the final state would be a Gibbs thermal equilibrium state, which is characterized by few conserved quantities like mass, momentum, and energy, and we all know that the form of this is the simplest form that you can write, and the approach to this state can be described by hydrodynamics. For example, to find out the evolution of the temperature profile in such a scenario, one solves heat diffusion equation. Now, what about integrable systems? So, integral systems are different from non-integral systems. They have extensive number of conserved quantity, which is extensive means it's proportional to the number of degrees of freedom, and they fail to thermalize to Gibbs state. And it is believed that upon coarse graining, they equilibrate to generalized Gibbs state, which generalizes this form, where instead of one Lagrange multiplier, you have many Lagrange multiplier for each for one conserved quantity, and all the conserved quantities appear here. Okay, and Z is the normalization of the distribution. And the corresponding hydrodynamics, in this case, one can write, and it's written in terms of quasi-particles, and they have the structure is known as generalized hydrodynamics. I will not be able to discuss that in detail. Now, the question that I want to ask is that if you have a system, integral system, and prepared in such a state that you have two GG state, they are different, and you bring them in contact, and what happens? What is the final stationary state? How does it go to that state? Okay. So this similar question, there are several other studies. For example, here, this is an experiment which describes so you prepare ultra cold Bose gas into two traps, double-L traps, and then suddenly switch off the confining potential and let the observe the evolution of the density. So it's like also you prepare the system in a non-equilibrium state and then observe its evolution and the evolution towards the final state. So such problems in general can be known as equilibration of thermalization problem, where you start from a non-equilibrium initial condition and you look at the evolution towards the final state, which is an equilibrium state. So in this talk, I'll consider only harmonic chain, and we consider two parts of the harmonic chain in two GG states, of course characterized by different set of these parameters. This side L, this side is R at t equal to 0, and look at the evolution at t at non-zero time. Okay, so the conserved quantities you can write down for harmonic chain, and they also have this kind of local structure where you have these conserved densities which satisfy continuity equations. So for example, the 0th one is the local energy, and then you can also write down for other n's, or other conserved quantities. Question is, how do they evolve? So let us consider a chain of infinite length and look at it on a coarse grain space-time scale. And in such coarse grain scale, these local densities become smooth functions, and the currents also, and you get a profile like this, and we want to understand what is the evolution of these profiles. Okay, so we consider two procedures. One is microscopic procedure and is hydrodynamic. Microscopic is easy because you can solve the equations of motion exactly, find out these quantities in terms of initial conditions, average over initial conditions, and then do coarse graining, and you get these profiles at final time. Hydrodynamic is you can do it from Wigner function. You know that in this case the Wigner function is simple. This is similar to the equation that what Abhishek also presented in the context of fermions, free fermions. And in this case, we actually can identify that this Wigner function has all the properties of the phase space distribution that one considers in Euler GHD, because one can identify it as a phase space distribution of quasi-particles. In this case, these are phonons, and one could also express all the conserved quantities in terms of integrals of these quantities, this distribution. So what we do, we from the initial statistical state, you can compute this and solve it and compute this. This is the simple procedure, and by which we compute these profiles. Let us consider the simplest case, which is we consider that these two parts are in Gibbs state, like only the temperature is different, all other Lagrange multipliers corresponding to higher conserved quantities are all 0. In this case, you have a temperature, step temperature profile at t equal to 0, and it evolves. And by solving the Wigner function, one can find out this solution, and this is how they evolve. So this is the initial profile, and this is at different times. This is at 0.01, 0.12, 0.18, and like this. And so basically the initial difference actually spreads, and it spreads ballistically. There is a collapse with space by time scaling. A similar problem was studied by Esler in the context of free expansion of free fermions on a lattice. So you prepare the lattice basically in this state where left half is filled initially. You create particles on each side on the left half of the particles, similar to initial condition that Abhishek was talking about in his page curve problem. And then he computed the density profile, and here also you get a similar profile. Only thing is that in this case you have a cos inverse. In our case we have sine inverse. It's a similar problem to that. Okay, so not only that, we can actually generalize to arbitrary GG state where all these parameters are different. And in that case also you can compute the conserved quantities, first conserved quantity and the second conserved. Actually, in fact, you can compute all the conserved quantities and also the associated currents. In this case, using this Wigner function, solutions of the Wigner function. Okay, and not only that, if you consider this problem in a finite system, you take the continuum limit by considering the lattice size going to 0. In that case, also you can compute the final GG state. So you have two GG states on two parts, and then let them evolve, and the system goes to a final GG state where it is also characterized by another set of parameters, and all these parameters can be computed. We have an explicit expression for those and the full distribution in terms of these parameters. And also we have computed how the system relaxes with time. I do not have time to discuss about those. So I think I have finished before the time. So okay. So the conclusion is that we have a coarse-grained Wigner function description, and that can be interpreted as a GHD equation for harmonic chain, as one can do for free fermions. And one can solve this GHD equation and to obtain explicit expressions for the time evolution of the density and current profiles starting from a non-equilibrium state. And we considered a particular initial condition, which is domain-level initial condition. We observed that the chain relaxes to the final GG state, which can be characterized by chemical potentials. And also the approach can be also described how. So actually in finite systems, finite size systems, it actually approaches as 1 over square root t. All the conserved quantities approaches to the equilibrium values as 1 over square root t, which I did not discuss. And we also can find out explicit expression of the final state. So thank you for your attention.
Questions? Yeah. So the time to reach the final GG state, is it very sensitive to the number of Lagrange multipliers in the left and right that you feed in, or is it more or less robust to number of Lagrange multipliers?
I think we have considered two cases. In one case, we have only one Lagrange multiplier non-zero and all others are 0. And another is in case we have two Lagrange multipliers non-zero and all others are 0. In both cases, in finite size system, we have observed that the approach is 1 over square root t in both cases. So yeah, but this is a good point. We should investigate more.
Comment that you cited for the free fermions, the density profile result by Fabian Esler, but actually it was computed much before that. Actually, it was Gunter Schutz who first computed, and then later on by Eisler and Ruck, and then many other people.
I see. I didn't know that. Thank you.
Let's thank the speaker once again.